All right, so today and likely tomorrow, we're going to be taking a look at section 6.2 in our text, okay? It's called Solutions About Ordinary Points. And each of these problems is going to take a very long time. And so I just want to be very upfront with us about that there are, I think, 3 practice questions in this section, but all 3 of them will take approximately 1 to 2 pages of work. So I just really want us to embrace that for what it is. Know that we're probably going to get through maybe 1 problem, maybe a little bit more than 1 today, and that is entirely okay. I'm more concerned that we are able to sort of think through the reasoning of this, what are our decision-making points along the way, and what characteristics we're looking for. I know that sequences and series tend to just be a really hard section for us, that it's something that is intimidating, and if it didn't go well, we sort of have this lasting impression that series are just terrible. And so it's almost like if you had a bad experience with trig, it kind of sticks with you for a while. I think series is kind of like the other big point in your math career where if it didn't really go that well, then it just sort of sticks with you as a bunch of symbols and letters, and it's really hard to make sense of, okay? But I think based off of the discussion questions that we've had and sort of the pre-thinking we've done around power series, my hope is that it'll be a little bit easier for us to focus on the bigger picture process that we're doing, okay? So what we know so far, we've talked about power series and something called shifting the index. And so keep in mind that when we did our shifting the index the other day, that was when we were looking at questions like if we had our sigma notation and there was an n equals 2 on the bottom, but we wanted to make it into something that was n equals 0. So that process is what I mean by shifting the index. Okay, that process we're actually going to use a lot in these questions, and we'll tie it back to this idea of the power series solution. Okay. But what's new, we're going to be taking a look at a new concept, one called ordinary versus singular points. And in particular, ordinary points are going to help us with 6.2, and singular points are going to help us with 6.3. Okay. That'll round out our experience with chapter 6. We'll be taking a look at ordinary points, singular points, and how they reflect in the different series that we have. And so today we're going to be looking at finding a power series solution, all right, to a specific class of differential equations. They are homogeneous, they are linear, and they are second order. Okay. All right, so that's where we're headed today. We're going to start with a little bit of an overview, okay? And so this is how our story begins. We have y equals this sigma, or the sum, from n equals 0 to infinity of a sub n x minus x naught to the n power. And we know that that is a power series, okay? And so just like before, we are going to assume, we are going to, assume a solution of that form. All right. So just like in one of our previous sections, we said, here's what we guess our y sub p to be, and then we could find y sub p prime, y sub p double prime. We're going to follow that same idea, except this time we're representing it with series, okay, and specifically power and Taylor series. So for example, all right, this is actually going to be our very first question that we look at today. Let's say we have this second order linear homogeneous differential equation, y double prime plus y equals 0. And we want a solution about x sub 0 equals 0. Okay, so that in fact would be our ordinary point that we're looking at. We're going to find out in, I don't know how long it's going to take us to get there, but we're going to get to this solution. Okay. And I wanted to put it up front, not to make you like sweat in your seat about like how difficult today is going to be, but rather just to kind of give us an idea of what our answer is going to look like, and that it's going to be okay, and that we're going to be able to figure out how we got from such a simple looking equation to such a complicated looking solution. Okay. Now, one thing that I do want to point out is that a series solution can only be found if the following is true. Okay. If x equals x naught, so that sort of center point, if you will, is an ordinary point. Okay, it's an ordinary point. And so the way our story is going to go today, we're going to assume a solution of this form. We're going to work through some steps. We'll try and highlight what those steps are. We're going to arrive at a solution that might look something like this. We should have sigmas in our solution. We should have x's and k's and coefficients in our solution. But all of this can only be done if that center point is what we call an ordinary point. Okay. And so that begs the question of, well, what in the world is an ordinary point, right? If this is what's so important to decide how we're going to apply this procedure, we should know what it means to be an ordinary point. Okay. And so let's go back, let's recall from a very long time ago when we first learned looking at differential equations. We said that we could have differential equations sort of that look like this, right? There's a coefficient. So a sub 2 of x, y double prime, a sub 1 of x, y prime, a sub 0, y equals 0. And then in order to obtain what we call a more standard form, all we did was divide through by that first coefficient, a sub 2 of x. And so what that means is that p of x could also be written as a sub 1 of x over a sub 2 of x. And that q of x could be written as a sub 0 of x over a sub 1, a sub 2 of x. Okay. So we divided things away. We called them a different letter just so that we wouldn't have to write a bunch of fractions. Okay. Now we're going to start with a case where our coefficients here are numbers. Okay. And let's imagine in the world of constant coefficients, numerical coefficients, what kind of a sub 2 value do you think would be problematic? Like, can you give me an example of something that would be a problem if we had that for our a sub 2? Good, exactly, right? If we had a 0 there, well, we wouldn't, because if we had a 0, we wouldn't have that y double prime, right? But if a sub 2 is 0, and we're looking ahead and saying we're going to divide by that, that's a big problem. Right? That's a problem for us because there's going to be points where things are going to be undefined. All right. And that, my friends, is precisely the difference between an ordinary and a singular point. All right. So let's see if I hide this space. All right. We'll write an ordinary on this side and singular on this side. Okay, so we have our ordinary and we have our singular. What we're going to do is we're going to define what it means to be ordinary. And then if you have any experience programming, you know, like if this is true, then great. Otherwise, it's not going to be that. right? And so our singular is going to be like, if it's not ordinary, it's going to be singular, okay? So if not ordinary, then it is singular, okay? So it would be really important for us to know what it is to be ordinary. And it is ordinary at this specific point, all right? So whatever we choose for that center point. And for us, we're gonna have that center point be 0 a lot, okay? We're gonna have that be 0 because it's a nice number. It turns a lot of our power series into a nicer form, okay, to work with. But it will be ordinary at this center point if P of X and Q of X, so those two coefficients that we got when we divided that A sub 2 away, if those two coefficients are something called analytic, right? Now, that was one of the terms that I said, hey, I just want you to like kind of read ahead and see what you think these mean, right? I didn't mean that you had to teach yourself what those mean. I just wanted us to do a little bit of pre-thinking so that when we got to this section, we would be a little bit more familiar, like, oh, I've seen that word before. Okay, so we have a point is going to be ordinary if P of X and Q of X are analytic. And what does that mean? Basically, that means that as long as P of X and Q of X are defined, okay, so as long as this coefficient and this coefficient are defined, we could, at x equals x sub 0, we can consider that an ordinary point, all right? And just like you all said earlier, this essentially means that that first coefficient is not going to be 0. Okay. Now, if A sub 2 of x is 0, then we're going to be saying it's singular. Okay, so on Thursday, when we meet to talk about 6.3, we'll notice sometimes that first coefficient will have places where it can be equal to 0, and that will make it a singular situation. Whereas what we're working with today and tomorrow is that they are ordinary. Okay. Now, it's easy for me to say, oh, singular is just not ordinary, but let me give you a couple examples of what we mean by singular. So for example, all right, let's say we had y double prime plus xy prime plus natural log of y, or x times y equals 0. So we've already divided my x sub 2 away, okay? Now we're checking, does this first term or this one, are they always defined? Okay. X, I would say, is totally fine. X is a linear function. It's defined everywhere. However, a natural log here, well, natural log is only defined between the values of 0 and infinity. There's no value at x equals 0. So this is not ordinary at x equals 0. Okay, it's not ordinary at x equals 0 because 0 is not included in the domain of natural log, right? There might be other values where it's not ordinary yet, but again, we're going to be focusing a lot on like when x does equal 0, just to make our computations a little bit smoother. Okay. And so that is our overview, as well as a quick definition on what it means to be ordinary versus singular. Okay. We are now going to dive into solving a problem. My goal for today is that we can solve a problem that we actually already know how to solve, But then we're going to solve it using this new method, and we're going to be able to come back and see how those two are actually the same answer. Okay. So let's begin. All right. So we have this example 0 here. Y double prime plus y equals 0. How do we solve that knowing techniques that, or using techniques that we already know? Don't be shy. Put out a response in that chat. Yeah, we have constant coefficients, right? We have a 1 and a 1 in front of there. And if that's helpful for you, write them in there. I'm not going to judge you for that. If that helps you make a decision that these are constant coefficients and therefore we're thinking a characteristic equation, by all means, please do that. Right? But this allows us to write the characteristic equation m squared plus 1 equals 0. Okay. And now we find our solution, right? Our roots are going to be plus or minus the square root of -1, which we know to be 0 plus or minus I. 0 plus or minus I. Now these are our roots. They are complex roots. So complex roots have a specific solution form. In fact, our solution, our y of x, is going to be e to the 0 times c sub 1 cosine 1x plus c sub 2 sine 1x. And I'm writing all the extra sort of numbers in here just so we can see that this 0 is that 0. And that this 1 and this 1 secretly come from, I should have written the 1 in there, 1i, right? This 1, that coefficient of the I gives us the number in front of the x in my sine and cosine, okay? Now I would fully expect that you simplify this, which is e to the 0, it's not 0, it is 1. And so we would say our solution y of x equals c1 cosine x plus c sub 2 sine of x. Okay. Look at the small amount of electric ink that we've used, right? This is like a 5-line problem at most. Now we're going to turn it into like a mazillion line problem. Isn't that fun? Okay. And in fact, y equals c sub 1 cosine x plus c sub 2 sine x, if I can make them on the same page, is actually equivalent to this monstrosity up here. How fun. Okay. So why in the world would we need to look at series solutions? Okay. The short answer here is if you are planning to take future differential equations courses, all right, you will be looking at Fourier series solutions. And in fact, that is very much a center point of partial okay, so the idea of a series solution is something that gets revisited in future differential equations courses. So if you're looking to be applied mathematics, that could certainly be something in your future. Okay, exciting, I know. All right, so how in the world do we solve this using a series? Well, we're going to break this down into 1, 2, 3, 4, 5 very long steps, okay? And we're going to start with step 1. And step one is we are going to check to see if x equals 0 is ordinary. Okay. Now I should have stated here that x sub 0 equals 0. All right, so just so we know that that 0 is going to be our center point. All right, I'm pretty sure I did that on the homework, but if I didn't, please let me know and I'm happy to update that. All right, so check to see if x equals 0 is ordinary. And so what we want to say is, do we have a sub 2 that is 1 or not 0? Okay, and here we can tell that this coefficient here is a 1. So that's one clue. All right, so one clue is that a sub 2, a sub 2 of x is 1, right? So that's one clue. But another clue is if I put a number like that invisible number that is in front of the y, I might notice there's a 1 there. And is there a value of x where 1 is not defined? And that's sort of a weird question to ask yourself, but 1 really means 1, right? It's a horizontal line at 1. And that, my friends, is always defined, right? There's no holes. It's not like I skipped a little bit and then kept going. If it's 1, it is 1 the whole time. Okay. So that's a sub 2 of x equals 1 is one clue. The second clue is that 1, there is no x value that makes 1 undefined. All right, and in particular, this 1 is our, what we would call our Q of x, right? It's always defined. And so therefore we know that this is ordinary about x equals 0. Okay, so here's what we can say about that. What this means is that y of x in a power series solution form, right? So our sigma from n equals 0 to infinity, a sub n, x minus x naught to the n. Instead of x naught, I'm going to put a 0 because that's the center point that I'm concerned about. If I have x minus 0, that's just going to be x, right? So we can actually make this into the sum from n equals 0 to infinity of a sub n x to the n. All right, and that is again because when we plug in 0 for x sub 0, that second term will go away. Okay. So in our check to see if it's ordinary, we actually get a guess for our solution form as well. The next step is we're going to find our y prime, and our y double prime. And then sub into our differential equation. Okay. This step should feel super familiar, like the kind we did when we went to the table and we said, oh, we guessed that it's going to be a cosine x plus b cosine x. And then we had to find the derivative and then the second derivative and then plug them all back in and see what makes it equal, right? This is going to be a lot more like that, except we'll just have a lot more things to write, okay? And so we already have our y, right? So we have y of x equals n equals 0, a sub n x to the n, right? Now you'll notice that I didn't write an infinity on the top, okay? Some schools of thought say you should always write that number on the top. Other schools of thought, depending on what resources you're using, may just drop the infinity and just say, well, we know we're taking an infinite series anyway, so we're just not going to write it, okay? It would, however, so I don't care whether you write the infinity or not, but I do care what this number is down here. So if you only write a sigma, but you don't have the number down there, you're gonna find it really hard to move past step 3, okay? So the number on the bottom of the sigma is actually super, super important, all right? All right, so let's go ahead and find that first derivative. And we sort of did this in 6.1 the other day, right? So we went ahead and we used the power rule. And so we were able to say that we're going to bring down a power. We're going to have times the constant and then x to the n minus 1, right? So that was us using the power rule here. But when we applied the power rule, what happened to the very first term, like our a sub 0? What happened to that term when we took the derivative?
It just became 0.
It just became 0, right? So in effect, we don't have n equals 0 anymore because the first term went to 0. So we compensate for that by writing n equals 1 on the bottom here. Because the a sub 0 term went to 0, so we just start counting from the first term, or from n equals 1, a sub 1. Okay. We take the derivative one more time. That's going to shift our index one more time to n equals 2. Because again, the a sub 1 from the first derivative, that's going to go to 0 because it's just a constant. And when I take the derivative of a constant, I get 0. But I am going to go ahead and bring down this power. So I'll get n times n minus 1 a sub n x to the, don't forget to lose another power, so n minus 2. Now I'm moving through these derivatives a little bit quickly because we did go over this in the 6.1 video. All right, so if you're looking at this like, I don't know where we're getting this from, please go back and watch that 6.1 video. We did spend some time talking about where these derivatives came from in a more laid out way, okay? But all of this is to say, we wanted to find these so that we could plug it back into our original differential equation. So we're going to need y double prime plus y equals 0. And so what is that going to give us? That is going to give us, so y double prime plus y equals 0. We're going to get the sum from n equals 2 of n minus 1 a sub n x to the n minus 2, right? So all of this, don't want to go overboard on the colors today, but this y double prime in series form looks like this. Okay. Plus, now we need to plug in the y. So plus sum from n equals 0 to infinity a sub n x to the n equals 0. Okay. So the orange part replaces the orange part, the green part replaces the green part. All right. So we've made sure that this is an ordinary point, and because it is, it allows us to proceed in this process. We find our y prime, our y double prime, we plug them into our differential equation, okay? So far, the process is the same, even though our notation may be a little bit different than what we've seen before. All right, let's see, how much room do I have left? Okay. I am going to grab these and just shrink them a tiny, tiny bit. Okay. All right, so our third step, okay? Our third step is this. We want to combine multiple series into a single series. Okay. We want to combine a multiple series into a single series. Meaning up here, I have an orange series and a green series, but I would like to get just one. I don't want two separate ones. I just want a single series. Okay. Now here's how we're going to do that. All right. These are two clues that I think are so important to look for. When you look at your series solutions, the one with multiple series, okay, in order to combine them, all right, if you think back to 6.1, in order to combine them, the index or the number at the bottom has to be the same. And right now they're different. I have a 2 and I have a 0. So I need to fix that. That is one thing I need to fix. The other thing I need to fix is I need to make x to the n and this one, I want those to be the same. I want them to both be x to the power of n. Okay. So what I'm going to do is I'm going to write this solution again down below, and I'm going to annotate like where the problem spots are so we know what we're trying to achieve. Okay. So if we have our sum from n equals 2 and n minus 1, a sub n x to the n minus 2 plus our second series. Okay, our problem areas are as follows. All right, want these to be the same. Okay, so right now they're different. We want them to be the same. And our second problem spot would be we want these two, want these to both be x to the n. Okay. That is our goal. Now, sometimes, as we'll see in this problem, because this is quote unquote an easier problem, okay? It's not easy. I don't want you to look at this work that we're about to do and say, she thinks this is easy. I don't think it's easy, but I think it's simpler than some of the other cases we'll see. Sometimes when we move one piece, like we make this equals n equals 0 by using our index shift, it fixes the other problem as well. Okay, so sometimes we're going to move one piece and it's going to fix the other piece in the same move. That will be the case in example number 1. But when we get to example number 2, we're going to move one piece. It's going to kind of change this piece, but not enough to fix the problem. And then we'll have to do something else to fix the second problem. Okay. So I just want us to be aware that what we're about to see magically happening is sort of a nice case scenario. Okay. All right. So in 6.1, I asked us to practice the idea of an index shift. right? And I noticed in the homework that people didn't necessarily write out like I equals this and N equals this. I would encourage you to do that because as you're doing these index shifts, now it's in the context of a bigger problem. We really want to make sure that index shift goes smoothly. Otherwise, the rest of our question might be a lot harder than we need it to be, okay? So in particular, I want to say that my index is N minus 2. Right? Because that's going to get this bottom number, 2 minus 2 is going to get me to 0. But it's also helpful to say, what is n? And n is going to be I plus 2. All right, so I plus 2 is what I'm going to substitute in everywhere in the first one. So we're going to get the sum of n equals 0. Instead of this first n, I'm going to write I plus 2. Instead of n minus 1, I'm going to write I plus 2 minus 1. Instead of a sub n, I'm going to write a sub I plus 2. And instead of x to the n minus 2, I'm going to write x to the I plus 2 minus 2. Okay. This is all still the orange solution, right? So all of this is the orange solution. I am doing an index shift on that orange solution. Plus, let me just write down the second part so I don't lose it or I don't forget that I have it. Okay. Now, this orange line that we just wrote looks pretty terrible, but let's actually do the arithmetic and see what it comes out to be. Let's see. Remember, we've shifted it, so now we can put that n back in. So n plus 2. The second brackets becomes n plus 1. This becomes a sub n plus 2. And this becomes x to the n. Plus the green, right? So we have orange plus green. Everything is in n's. Let's see if we addressed the problems that we identified in the beginning. So the first problem we said was, hey, these numbers at the bottom should be the same. Well, we made it so that this one is n equals 0 and this one is n equals 0. So we've checked that off the list. That's good. Okay. Now, we wanted both the powers to be the same. In fact, we wanted them to be x to the n. And as I said, sometimes we're lucky. We were able to get x to the n in both of them. Okay. Now, why is this important? The fact that we have the same index and x to the n means we can now combine our multiple series into a single series, right? And this too, we talked about when we were adding and subtracting series in 6.1. And so here's how these pack up into a single series. They both start at 0. Okay, they both have the x sub n, but once we factor out the x sub n, basically we take this clump and we add it to the other one. In other words, we have n plus 2 times n plus 1, a sub n plus 2 plus a sub n. And then I factor out my x to the n. Okay. All right. So I want to pause here for a moment because we've done a lot of writing. I've done a lot of writing, which I know means you've done a lot of writing as well. Let me zoom out so we can kind of see what we've written so far. Let's see if there are any questions before we move on, because we still have a very long step 4 and a very long step 5. All right. Well, there was another question that I asked you to think about in the discussion last week. And that question, or in the homework last week, and that question was, let's say that you have something like that, right? The sum of your series equals 0. And this is the last question on homework 5, I think. My question was, what is true about all the coefficients? Like, what's true about a sub n? And the answer that I was looking for is the only way that this is true, all right, because the x to the n's are not going to be equal to 0. This is only true if the coefficients equal 0. Okay. This is almost like a parallel of this question. Right? When we learned how to factor a really, really long time ago, and we said, well, if you factor and we're multiplying all those things, the only way that can equal 0 is if each of the parts equals 0. And so we're extending this idea to a series where if the sum of all the terms in the series equals 0, then those coefficients must equal 0. Okay. All of this combining multiple series into a single series, this step down here, look at what we can say. We can say that that whole clump in front of x to the n has to equal 0. In other words, this whole clump, the thing inside the brackets, that has to equal 0. And that is going to be what helps us solve this problem and get it into that very complicated form that we saw back in the overview part. Okay. All right. These questions are so long. I'm going to add a page. Okay. So we want to say that I want to write that in a different step. Sorry. All right. So step 4. Okay. We're going to solve the recurrence relation. And this, I think you've all taken discrete, yes? So 245, no, okay. I think it does maybe depend on the, on which school you are in. What did I want to do? Okay, but the recurrence relation is a concept from Math245. Okay, but if you haven't had 2 to 45, that is absolutely fine. All right, The basic gist of it is we're going to take this thing in the brackets. We're going to set it equal to 0. Okay. So we're going to take n plus 1 times n plus 2. Whoop. Other way. N plus 2 times n plus 1, a sub n plus 2 plus a sub n equals 0. Okay. Let me know if the grid lines bother you. I can certainly take the grid lines off if that doesn't feel like it's easy on the eyes. Okay. But we have this as our recurrence relation. Okay, so when we say recurrence relation, we mean that clump inside of the brackets. We're going to set that equal to 0. And what we're going to keep in mind is that we'll usually have a sub somethings, but what we want to do is solve for the a with the bigger something. Okay, that was like the least mathematical way I could have said that, but see how n plus 2 is bigger than n? I want to get a sub n plus 2 by itself. Okay. So we might say solve, isolate a to the bigger value. Okay, and so in this case, if we get a sub n plus 2 by itself, absolutely, I can do that. Thank you for letting me know. All right, that better? Okay, cool. All right. So if I wanted to get a sub n plus 2 by itself, what would be a good first step? Like I bet in 2 steps, we could get this a sub n plus 2 by itself.
Subtract a sub n from both sides and then divide by n plus 2 times n plus 1.
Perfect, right? So it's like a very grown-up way of looking at equation solving. We're going to still follow our order of operations. I'm going to subtract that a sub n. So if I were to write this out, let's write n plus 2, n plus 1, a sub n plus 2 is going to equal negative a sub n. And now I just want to divide by the things that a sub n plus 2 is multiplied by. So I will get a sub n plus 2 equals negative a sub n over n plus 2 times n plus 1. Okay. We also want to be really specific here that this is for n that is all positive integers, right? So we're looking for values of n that work, right? Actually, z plus technically doesn't involve 0. So another way you might see this is like 0, 1, 2, dot, dot, dot. Okay. Okay, so we've solved this recurrence relation, but this step 4 actually entails a lot of pattern finding. Okay. This is the part that I think is easiest if you write out a lot of examples. No one will judge you for how many examples you need to write compared to how many somebody else needs to write. Okay, that's not the game here. The game here is to find the pattern and to be willing to write out as much as you need to find said pattern. Okay. Now I'm gonna sort of write this in a way that maybe as I'm writing it, you're like, why would she organize it that way? But I think at the end of this, we'll see why it was organized that way. And it's okay to not know right off the bat. You can also just go right in order. And then after you've written enough terms, go back and see what kind of patterns you might see. Okay. So it's usually best to start with n equals 0. Okay. And so we're going to take n equals 0, and we're going to plug it into our recurrence relation. Okay. So if n equals 0, that means I have a to the 0, or a sub 0 plus 2 equals negative a sub 0 over 0 plus 2 times 0 plus 1. Okay, so when we find a value for n, we literally plug it in everywhere we see an n. And that's weird for folks because sometimes it means it's a number and sometimes it's the subscript. Okay, and so I would really encourage you to be very careful about your notation. All right, no shame in taking like 18 pages of work to write this out so that you can stay organized, so that you don't make mistakes. Okay. But it is nice once we've plugged things in to kind of simplify what we can. And so in this case, I could write a sub 0 plus 2 as just a sub 2, right? 0 plus 2 gives me 2. And then I have my minus, that doesn't change. A sub 0 is fine. Now I'm going to be really particular about how we simplify the denominator, okay? You'll notice that I never FOILed this out. I didn't multiply it out. I left it as it is. And that's one of the things that, while being able to multiply polynomials is an important skill, it doesn't mean that every time we see that, we should do that. And in fact, the higher you get in math, the more likely it is that an unsimplified version will help you see the patterns better. Okay, so here's what I mean by that. I know that 0 plus 2 is 2 and 0 plus 1 is 1. And I know that 2 times 1 gives me 2. But I'm going to write it like this, 2 times 1. Okay, and we'll see why in just a little bit. Now, in finding my pattern, the next value I actually tried was n equals 2. Okay, and again, we'll see why that is in a little bit when we get to the other values of n. Okay, but if I plug in n equals 2, I'm wondering if you can tell me what my recurrence relation will be. Okay, so take a moment, plug in 2 everywhere you see an n, simplify it in the same flavor that we did for n equals 0. Okay, and when you get that, go ahead and throw that into the chat and let's see where we have. Ooh, super close. There's one small change to that, but I love what you have. Oh gosh, a sub 4 equals, let's see, negative a sub 2 over 2 plus 2 is 4. I agree with that, but 2 plus 1 is going to give us 3. Yeah, so we'll just change that last 2 to a 3. All right, so I hope we're all getting this as our a sub 4, right? It equals negative a sub 2 over 4 times 3. Okay. Now let's try one more. Okay, let's try one more. Let's go with n equals 4. So go ahead and plug in n equals 4, and let's see what we get from our recurrence relation. Right, and again, once you find that, go ahead and throw that in the chat. Okay, so it looks like we're getting a sub 6 equals negative a sub 4 over 6 times 5. Okay. Now, I bet if we keep going with sort of the even values of n, like 0, 2, 4, 6, blah, 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 we would start to see some sort of pattern, okay? But what I don't love about this pattern is that the first one deals with a sub 0. So in order to find a sub 2, I need to find a sub 0. And in order to find a sub 4, I need to know a sub 2. And in order to find a sub 6, I need a sub 4. And so it almost feels like I need to know the one that came before in order to find out the one that comes next. However, it turns out we can be really clever in these situations. I already defined a sub 2. In fact, I said that a sub 2 equals negative a sub 0 over 2 times 1. Everywhere I see an a sub 2 in the other term, I'm going to go ahead and replace it with this. And so what I get is negative a sub 0 over 4 times 3 times 2 times 1. Or I could say this is simply a sub 0 over 4 factorial. The beauty about this is now, if I know a sub 0, I can find a sub 2. But if I know a sub 0, I can also find a sub 4. And we can sort of repeat this process. Instead of writing a sub 4, I'm going to write it as a sub 0 over 4 factorial. Now, if I know a sub 0, I can find a sub 2, a sub 4, a sub 6. If I kept going, I could find a sub 8, a sub 10. I could find any even value of that subscript. Let me ask you, based off of this pattern you see here, what do you think a sub 8 is going to be?
It would just be negative a sub 0 over 8 factorial.
Close, close. I do believe that denominator is going to be an 8 factorial. That matches the pattern. I agree that there's going to be an a sub 0. Thoughts about the sign of this? Because we've got a -1, a +1, a -1. I bet this next one is going to be positive. Okay. Cool. A sub 10, is that going to be positive or negative? Yeah, that's going to be negative, right? So in other words, it's going to be alternating signs, all right? Now here is where I think things are a little bit tricky, all right? But you've done such a great job in identifying the pattern. Let's write down the characteristics of this pattern. So I think that they all look like some sort of fraction with a sub 0 on the top, right? Every single one of these has an a sub 0 on the top and some other number on the bottom. Like that's a pattern that I see. Can anyone tell me how I might predict what this number in the bottom is going to be? Okay. So whatever this number is, right, n plus 2, it's going to be that number factorial. Okay, good, good. So it's going to be some sort of factorial. All right. The last pattern that we might notice is that the signs alternate, right? Positive, negative, positive, negative, positive, negative. And so here we're going to take these 3 clues and we're going to write a general statement about all of the even terms. Okay. So let's write this in blue. So for any term that has an even subscript, okay, so 2k is a very common way of saying even, because you can take any number you want, and if you double it, you're going to get an even number, right? So like 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6, right? No matter what number you put in there, 101 times 2 is 202. That's an even number. And so as mathematicians, instead of writing a sub even number, we write a sub 2k. And it turns out that we know we're going to have a fraction. That's right. We know we're going to have a fraction. We know we need to know a sub 0, right? And if we want to refine what Elliot said about that factorial, let's notice something for a moment. This is 2 and this is 2 factorial. This is 4 and this is 4 factorial. This is 6. This is 6 factorial. This is 8. This is 8 factorial. So if I have 2k, how would I write that in the denominator? Exactly. We're going to have 2k factorial. Okay. That takes care of the a sub 0 is all we need to know. And then we divide it by that factorial. The last thing we need to incorporate into here is this alternating sign situation. Does anybody know what the common way of saying alternating signs is, like in an equation? Good, good, good. We take -1 and we raise it to a power. Now we'll notice that everything in here has k's. So I'm going to make one small modification to Robert's answer. We're going to do -1 to the k power. All right, so that -1 to the k, that does the alternating signs. And actually, let me highlight these. So I think that's actually a worthy of some highlighting. Okay, so alternating signs is this piece right here. So you want to alternate a sign in an equation, you do a -1 to the k power, that'll alternate signs. You want to think about that factorial number, right? That's this 2k factorial on the bottom. And then our a sub 0 is the one constant piece in every single one of these that we wrote here, right? Every single one of them we could reduce to something with an a sub 0 in it. And so look at this and let's see what we have. A sub 2k equals -1 to the k, a sub 0 over 2k factorial, right? We should see pieces of that in our final answer, right? In fact, if you scroll back up and you compare this to the answer I told you you were going to have at the end, pieces of this should be in there, okay? Now, we found a pattern for all the even ones. Well, if they're even numbers, we also got to take a look at the odd numbers, okay? So we're going to go back through. We're going to try the same idea. We're going to look at values n equals 1, n equals 3, n equals 5, and see what kind of patterns we can find. We're going to list out those patterns, and then we're going to figure out how to put those patterns into an equation, okay? So n equals 1. If we put this into our equation from above, we will get a sub 3 equals negative a sub 1 over, let's see, 3 times 2. Now, if you got the hang of the even ones, plugging in for the odd ones is not really different, right? It's the same idea. And we want to also simplify accordingly, right? We don't want to oversimplify. Turning that denominator into 6 might ruin the pattern for us, okay? We're going to do the same thing with n equals 3 and n equals 5. Okay, so I'll give you a moment to fill those out. What is a sub 5? What is a sub 7? And if you can turn everything into something like maybe with a sub 1, that would also be a really good next step. Okay. I'll give you a few moments to figure out those two terms, a sub 5 and a sub 7. And then we'll see what kind of patterns we come up with. Right, and for the sake of time, I'll start to write some of this out. Right, and just by doing each one by itself, we should end up with the following 3 expressions. But if we keep in mind that everywhere we see a sub 3, we can actually plug in something else for it, and we do a little bit of substitution, we'll end up with And for a sub 7, we'll end up with now I noticed that in our previous problem, with the even ones, we had the full factorial, right? 4 times 3 times 2 times 1 is 4 factorial. 6 times 5 times 4 times 3 times 2 times 1 is 6 factorial. However, 3 times 2 is actually the same as 3 times 2 times 1. So we could actually rewrite this as negative a sub 1 over 3 factorial. That's really ugly a, hold on. And that means we could write a sub 5 as a sub 1 over 5 factorial, right? Because 5 times 4 times 3 times 2 is the same as 5 times 4 times 3 times 2 times 1. And the last one we wrote, we can write as negative a sub 1 over 7 factorial. Okay. And so if you wanted to, you could write more of these. There's no harm in writing more of them, right? There's no judgment in writing out 10 of them to find the pattern. Okay, some patterns are harder to find than others. But of the characteristics we said for the even ones, are there any we feel like we need to change? And if so, what are the things that we might need to change? Yep, we want to change a sub 0 to a sub 1. Good. So maybe we write a sub 1 over a number. Okay. I think that the signs still alternate, right? Negative, positive, negative, positive. So that part is going to stay the same. Right. Now, in our final answer, we wrote like a sub 2k. And the 2k was there to describe a sub any even number. So how do we modify that if we want to say a sub odd number?
Do 2k plus, well, I guess, or minus 1.
Exactly. All right. So different, you can always say for an odd number, you can use 2k plus 1 or 2k minus 1. I think depending on the case, more times it is useful to have the 2k plus 1, but occasionally you'll find it more useful to have 2k minus 1. Okay. But if we write this out, we'll say a sub 2k plus 1 equals, we want the alternating sign, so negative 1 to the k, that part is going to stay. But instead of a sub 0, we're going to write a sub 1. And in the denominator, we're not going to have 2k factorial, but we'll have 2k plus 1 factorial. All right. All right, so step 4, a very lengthy step that involves finding patterns and being able to generalize those patterns in a much more succinct way. Okay. Now we've got about 8 minutes left. I believe we can finish this problem. I would like to at least finish writing it down, but tonight, if you look over them and you're like, ooh, I don't know where this step came from or how we got from this to this, let's come back and revisit that tomorrow before we start example 2. Okay, so the goal, I think, for these last 8 minutes is to finish writing this so you have a complete solution for one, and then we'll come back tomorrow and see if we can sort of answer any of those questions. Okay. All right, so our step 5 here, after we've solved these recurrence relations, is we are going to write our solutions. I'm going to write our solutions. And so remember, we guessed originally that we would have y of x equals the sum from n equals 0 to infinity of a sub n x to the n. That was our guess, right? All of this has been around that as our solution. Well, I want to take the time to write out what all of these terms mean, right? Sometimes series form is hard to imagine, but when we expand it, we can identify those patterns, regroup or reclump, and then put them back together in a series solution, okay? So here's what I mean by that. If I were to start writing out the terms, I would get a sub 0 x to the 0 plus a sub 1 x to the 1 plus a sub 2 x squared plus a sub 3 x to the 3rd plus a sub 4 x to the 4th plus I'll basically have some even term and then an odd term along the way, right? So I expanded out, I realize I've got even, odd, even, odd, even. All right, I keep going. At some point, I'll pick up another even one and I'll pick up another odd one, right? And so even and odd is actually a really nice way to split series, okay? There's a question in the chat there. What's your answer? Is cosine even or odd? Yeah,
cosine's even.
Mm-hmm. Is sine even or odd?
Sine's odd.
Oh. Okay, so when we answered this question in like less than 5 lines, we came down to a c sub 1 cosine of x plus c sub 2 sine of x, meaning we had some even solutions and we had some odd solutions. Another way of thinking about our even and odd is that when we look at all of these, we're going to have some even and some odd. All right. Now, let me go ahead and replace, like, for example, instead of a sub 2, I'm going to go ahead and write negative a sub 0 over 2 factorial. And anywhere I see an a sub 4, I'm going to write a sub 0 4 factorial. And everywhere I see an a sub 3, I'm going to write this, a sub 5. Okay, so I'm going to substitute in what I found from my stuff above. That's going to give me a sub 0 plus a sub 1x minus a sub 0 over 2 factorial x squared minus a sub 1 over 3 factorial x cubed plus a sub 0 over 4 factorial. Skip a few, right? At some point later down the line, I'm going to have something even and something odd. And we're going to group all of the even terms together, and we're going to group all of the odd terms together. So it's like a very grown-up clumping of your terms, right? So even, 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 and odd, odd, odd. Now, all of the even terms all the ones underlined in the pink, they have an a sub 0. And all the ones in the orange have an a sub 1. And so I'm going to go ahead and all the pink ones, all the even terms, I'm going to go ahead and pull out that a sub 0. So when I factor out an a sub 0 from here, I'm going to have a 1. When I pull out an a sub 0 from here, I'm going to get negative x squared over 2 factorial. When I pull out, oh, I forgot x to the 4th. When I pull out an a sub 0 from this, I'm going to have x to the 4th over 4 factorial. I'm going to repeat the same process for my a sub 1. So a sub 1 gets factored out to the front. Let's see what we have left. I have x minus x cubed over 3 factorial. The next one would be plus x to the 5th over 5 factorial. And I would keep going by grouping all of the odd terms. Okay. Now this is very similar in structure to this. The only difference is that these ones are multiplied by x to some power, right? It has this extra x to some power here. So the way we take care of that is we say this, a sub 0, the sum from k equals 0 to infinity of, we're changing our signs. We are doing the coefficient factorial. And then we have times x to that even power. We do the same thing for the odd ones. We get a sub 1, the sum from k equals 0. Same thing, we're going to alternate signs. That's negative 1 to the k. But instead of x to the even power, we're going to have x to the odd power over that odd number factorial. That, my friends, is our solution. Our series solution for this differential equation. And if you go ahead and look up the Taylor series for cosine, you'll find that it looks like that. And if you go ahead and look up Taylor series for sine, you'll find that it looks like this. And so in a much more grown-up way, we have our c sub 1 cosine x and our c sub 2 sine x. All right. So my friends, I know we are over time, so I'll leave this here in case anyone wants to take a quick screenshot, but then I'll go ahead and post these notes and video right now. Okay, so thanks for sticking around. Have a great rest of your day and definitely come back for part 2 tomorrow because we're going to do more examples just like this. Okay.